Far beyond the Sun, over 30 times its distance away, lies a remote and enigmatic celestial body on the outer fringes of our solar system. Neptune. This distant ice giant remains shrouded in mystery, concealed from the naked eye and discernible only through telescopic aid, even from the highest vantage points on Earth. Neptune, due to its vast remoteness, stands as the least explored entity within our cosmic neighborhood. But what is it about this distant planet that makes it so enigmatic? Would it astonish you to learn that Neptune, one of the coldest members of our solar system, possesses the capacity to harbor a scorching, hot ocean? Today, we embark on a journey to uncover the secrets of Neptune, delving into its peculiar rings, its mesmerizing azure hue, and the latest revelations about its renowned satellite, Triton. Neptune, an ice giant, dwarfs Earth, spanning 4 times its width with a radius of approximately 15,300 miles and a volume of 15 trillion cubic miles, making it a colossal entity and also 58 times Earth's volume. This celestial body is predominantly composed of water, methane, and ammonia, and like other gas giants, lacks a solid surface. Its atmosphere extends deep into its core, comprising methane and ammonia ice, enveloping a rocky core, despite its frigid location in the outer reaches of the solar system. Neptune has been the subject of intrigue due to its potential to host an internal, superheated ocean. This curiosity arises from the question of how such an ocean could be sustained, given that it takes sunlight a staggering 4 hours to reach Neptune's surface. With an average atmospheric temperature of 360 degrees Fahrenheit, Neptune stands as one of the coldest entities in our cosmic neighborhood. Recent research has unveiled that most of Neptune cooled between 2003 and 2018, though it experienced warming near the South Pole from 2018 to 2020, attributed to seasonal shifts in atmospheric chemistry. The precise origin of this hypothetical ocean within Neptune remains elusive, with scientists proposing several theories. Some posit that it may be due to heat generated by gravitational compression or interactions between Neptune and its moon, Triton. However, researchers Sloan Viktorovich and Andrew Ingersoll believe that the likelihood of an ocean arising from internal heat is currently a mere 15%, with a potential increase to 40% over the span of 1 billion years as the giant cools. Another intriguing hypothesis suggests that Neptune may have collided with a cosmic object, as it emits nearly 3 times the energy it receives from the Sun. This theory aligns with its unusual 28-degree axial tilt, reminiscent of Earth's, resulting in distinct seasons, albeit with each season spanning approximately 40 Earth years, while a single Neptune year equates to 165 Earth years. In contrast, a day on Neptune lasts a mere 16 hours, generating immensely powerful winds, a topic we'll explore further. Neptune's atmosphere is primarily composed of hydrogen 80%, helium 19%, and a blend of other gases, including methane approximately 1%. Interestingly, it is the presence of methane clouds in the upper atmosphere that imparts Neptune with its striking blue color. Methane molecules absorb shortwave solar radiation, reflecting a blue hue. However, Uranus, the closest planetary neighbor to Neptune, boasts a similar gas composition but exhibits a paler shade of blue. Dr. Patrick Irwin of Oxford University speculates that this divergence may be due to variations in methane fog density, giving rise to distinct aerosol layers. Neptune's atmosphere contains multiple aerosol layers. The lowermost layer consists of hydrogen sulfide ice, contributing to darker areas, particularly near the poles. Above it lies a haze particle layer likely associated with methane ice, which can precipitate as methane snow. Neptune's active atmosphere efficiently produces this snow, contributing to its rich blue hue. The uppermost layer also features methane ice particles and essentially extends the second layer. Beyond its vibrant color, Neptune bears dark and white patches across its surface, each signifying a storm generated by its rapid axial rotation. With wind currents reaching up to 1,200 miles per hour, nearly 4 times stronger than Jupiter, Neptune claims the title of the windiest planet in the solar system. Among its tempests, a massive storm, aptly named the Big Dark Spot, made its debut in 1989, observed by the Voyager 2 spacecraft. However, this colossal cyclone, equivalent in size to Earth, displayed a relatively short lifespan of 2 to 6 years. In 1994, the Hubble Space Telescope detected the storm's disappearance and the emergence of a smaller cyclone in the northern hemisphere. In 2018, the Hubble once again identified a new storm reminiscent of the 1989 event. These storm formations, shrouded in mystery, intrigue scientists. They are thought to originate deep within Neptune's atmosphere, evolving over years. Moreover, in 2018, the newly identified storm displayed an unexpected change in direction, adding to the enigma. Researchers speculate that the small vortex accompanying the main storm might play a role in the larger storm's eventual dissipation, a phenomenon never observed before. Such cyclones, accompanied by swiftly moving white methane clouds called scooter clouds, likely form over vortices where gases freeze into ice crystals, offering insights into the creation of patches on Neptune and similar ice giants. Like other gas giants, Neptune possesses a ring system. In 2022, the James Webb Space Telescope provided a near-infrared glimpse of these faint rings and accompanying satellites, marking the first imaging of Neptune's rings in over 3 decades. Approximately 5 rings are discernible in this image, each named in honor of astronomers who contributed to Neptune's study. Among them, the Halley ring stands as the innermost and most diffuse, comprising 40% to 70% dust and spanning 26,000 miles with a radial width of 1,240 miles. Next, the Leverrier ring is more substantial and brighter, though somewhat narrow, measuring just over 62 miles in width. The Lasso ring, the widest of them all at 84 miles, contains a small dust fraction, 20% to 40%. The Arago ring, challenging to perceive, possesses a radius of 35,540 miles and a minimal dust presence. Finally, the Adams ring, with an orbital radius of approximately 39,724 miles and a mere 35 kilometers in width, stands as Neptune's narrowest ring. Unique to Neptune's Adams ring are its arcs, bright regions of dust that encircle the ring's perimeter, each bearing a distinct name: freedom, brotherhood, courage, and equality. Remarkably, these arcs are not static and exhibit dynamic material exchanges and size variations, further mystifying their formation. One theory posits that the arcs may arise from the disintegration of a parent body or another object within the Roche limit. In addition to the rings, the James Webb Space Telescope captured images of 7 of Neptune's 14 satellites, classifying them into regular and irregular categories. These satellites play pivotal roles in Neptune's ring dynamics, with some, like Despina and Galatea, serving as shepherds for the ring dust. Among Neptune's moons, Triton stands out as the most remote and intriguing. Larger than Pluto, Triton boasts a diameter of 1,680 miles, accounting for a staggering 99.7% of the total mass of Neptune's moons. It is also the coldest geologically active body in the solar system, with surface temperatures plummeting to 391 degrees Fahrenheit, primarily due to its highly reflective icy exterior. Triton's peculiarity extends to its orbital characteristics as it moves in a retrograde orbit. Unlike other moons in the solar system, this means Triton orbits in the opposite direction to Neptune's rotation, causing its poles and equator to alternately face the Sun. Triton's odd orbital tilt likely originated from its capture by Neptune, possibly as it traversed the Kuiper belt. This unique orbital arrangement prevents it from colliding with Neptune and could explain the limited number of moons around Neptune compared to Jupiter. Exploring Triton's surface reveals a mosaic of features, with cryovolcanic plumes, craters, and smooth areas, suggesting relatively young terrain, possibly formed within the last 10 to 100 million years. Some regions hint at cryovolcanic activity, raising the possibility of a subsurface ocean. Triton's plumes may result from solar heating, causing nitrogen to escape from beneath its icy surface and forming a thin nitrogen atmosphere. Yet the potential for life on Triton remains uncertain, as its origin in the Kuiper belt makes it a unique and complex celestial body. Triton's presence also raises questions about the influence of Neptune on objects in the Kuiper belt, which marks the boundary of our solar system. This region, comprising asteroids and numerous large objects, including dwarf planets like Pluto, extends from Neptune to about 30 astronomical units and is integral to the origin of comets. Some Kuiper belt objects, including Pluto, exhibit long-term resonance with Neptune, hinting at the potential for Neptune's migration from its original position closer to the Sun. Such migration may have prevented these objects from being ejected from the solar system, ultimately impacting the dynamics of our cosmic neighborhood. Neptune remains a realm of uncharted mysteries, with many aspects of its composition and formation still veiled in uncertainty. Future scientific expeditions hold the promise of unveiling the chemistry and enigmatic secrets of this distant ice giant, shedding light on the intricate workings of ice giants in our celestial realm.